Next, our discussion hinges around some of the properties of matrices. Many of the properties of real numbers also hold true for matrices. A summary of these properties are listed below. The properties that we have on real numbers, the commutative, associative, and distributive property, also hold in matrix operations. Just a quick review of the commutative property. The commutative property says that we can add them in any order. So with real numbers, we're saying that we could take 2 plus 3, it will be the same as 3 plus 2. There's no difference. And when we add matrices, we're adding corresponding elements, so it doesn't matter what order those elements come in, we should get the same answer. The next one is the associative property, and the associative property says it doesn't matter about your grouping. So this one is your grouping property. So if I group A and B first and then add C, it's the same thing as if I add B and C first and then add A. So in this example, we could go 2 plus 3 plus a 4 should give us exactly the same result as if we take a 2 plus a 3 plus 4, but this time we change our grouping and then 3 and 4. The same result, and you can do the quick addition there, the same result. We get the same result either way. So one of them is we can change the order. So this is an ordering one without changing our answers in our matrix. And the other one is a grouping one. The distributive property says that we can distribute our scalar through our addition. So we go ahead and multiply matrix A times K, and then multiply matrix B times K, and get the same answer as if we were to add A and B first and then multiply times K. And it doesn't matter if the scalar multiplication is on the left or the right. Multi-step operations can be performed on matrices. The order of these operations is the same as with real numbers. Now, my interpretation on that, if the order is performed the same on real numbers as it is in matrices, that means we want to apply our acronym of PEMDAS, which, if it were me, I would have named GEMDAS, so that I encounter and get all the grouping symbols in our order of operations. So in our first example they give us here, we're supposed to take 4 times the sum of P plus Q. So that's going to be 4 times the matrix that we create when we add P and Q together. So we're going to add P and Q together, so that's a -1, 8 and 5 is 13, -2 and 7 is a 5, and then we've got a -2, -5, and a -10. Then we want to take this matrix and multiply it times 4, so we have our scalar multiple out there. And now our new result, well, different color, is a -4. And 4 times 13 is 12, carry the 1, that should be a 52 and 20. -8, -20, and -40. It's an ugly matrix symbol, let me clean it up. That is our final matrix on the 4 times P plus Q. To illustrate the property, the distributive property, the scalar distributive property, what I'm going to do is I'm going to redo this problem a second time, only this time I'm going to go and use the scalar property. So if it's 4 times P plus Q, we can get the same result of if we take 4 times matrix P and then add it to 4 times matrix Q. So we're going to do the multiplication here, and then we're going to do the addition. So 4 times matrix P, so it's going to be 4 times 3, which is 12. 4 times 8 is 32. 4 times a -2 is a -8. -20, 20, -16. We want to add that to 4 times Q. Now 4 times Q is going to give us the matrix -16, 20, 28, and then our next one is 4 times 3, which is 12, 4 times -10, which is -40, and 4 times -6, which is -24. And then we're going to add our 2 matrices together. So I got a 32 there. So when we add them, the 12 and the -16 is a -4. The 32, which is hard to read, and the 20 gives us 52. The -8 and the 28 gives us 20. The -20 and 12 gives us a -8. And the 20 and the -40 gives us a -20. A negative 16, a negative 24 is a negative 40. So whether you use the distributive property with the scalar, or if you go ahead and add first and then multiply by your scalar 4, you should get the same result.